All right, guys, welcome back. We're going to go over some waves things, which is really just how to go from one graph to another. The diagram on the right shows a block attached to a Hookean spring, so that tells us it's an ideal spring. On a frictionless surface, the block experiences no net force when it's at position B. When the block is at the left of point B, the spring pushes it to the right. When the block is at the right of point B, the spring pulls it to the left. The mass is pulled to the left from point B to point A and then released. The block then oscillates between positions A and C. Assume the system consists of the block and a spring and that no friction or dissipative forces act. So this dissipative forces would be non-conservative forces like friction and air resistance. The block undergoes simple harmonic motion with constant amplitude. What three conditions must be met for simple harmonic motion? You must have a restoring force. You need to have a displacement that is proportional to a negative acceleration. And we have to have a sinusoidal function of position. All right, so our conditions for simple harmonic motion is that we have to have a restoring force. Make this smaller. Our acceleration and displacement are in opposite directions. And our acceleration and displacement are directly proportional. The block takes 40 seconds to make 20 oscillations. What is the period of oscillation? So the period is 1 over the frequency, and it's the time for one oscillation. So if 20 happened in 40, it would be 2 seconds. When the block is moving from B to A, in what direction is it accelerating? So when it is going this way, acceleration's always in the same direction as the net force. So when it's going from B to A, if I did a free body diagram on it, it would have a spring force that's pushing it that way because it is compressing a spring force, right? Spring force is always going to be in the opposite direction as the displacement. And it has a normal and it has a weight. So since F of S is to the right, so is A. Right? Force always is going to agree with our acceleration. What is the frequency of this system? So frequency is going to be 1 over T. So 0.5 hertz. What is the amplitude of vibration? Amplitude is the original displacement, how far it was displaced. So looking at this, it tells us that it is displaced the whole thing's 40 centimeters, so that would mean that the displacement is 20 centimeters. So 0.2 meters would be A. So the formula for our motion, remember that our angular frequency is 2 pi over t, which this is 2 seconds. The formula for this would be 0.2, because that's my amplitude, cosine of pi t. What would happen to the period and the frequency of the system if you were to double the amplitude? Nothing. This is our formula, and amplitude does not show up in it. What would happen to the period and the frequency of this system if you were to double the mass while keeping the amplitude and spring the same? Okay, so the period would change. I'm going to put in ones for everything that doesn't change. So even though it's a 2 and a pi, I put in ones. We're saying the mass changes. K doesn't change. So TS would increase by radical 2. And then frequency is 1 over that. So it would change by 1 over radical 2. All right, so the graph above was created by placing a motion detector below a 100-gram mass oscillating up and down while hanging on a spring of unknown spring constant. What is the frequency of oscillation for this mass spring system? So my period, geez, they don't give us nice even numbers, do they? Let's just count how many cycles I have. So 1 cycle, 2 cycles, 3 cycles, 4 cycles, and 4 cycles takes 3 seconds. So 4 cycles per 3 seconds would be 0.75 hertz. What is the value of the spring constant for this spring? So if my frequency is 0.75 hertz, my period is going to be 1 over this value. So my period is 1.25 seconds. And I know what my mass is, which is 100 grams. So I would have that T is 2 pi square root of m over k. I would square both sides. Then get k by itself. I would convert my mass to kilograms. And hope that I had a calculator handy, right? Because this you definitely need a calculator for it. So 4 pi squared times 0.1 divided by 0.125 divided by 1.25. I got 2.5 newtons per meter. The position versus time graph. below describes the motion of the system on page 1 for 4 cycles. Complete sketches for the other graphs as shown based on the position versus time. All right, so to go from position to velocity, so you're going to take the slope of xt to get vt. So find zero slope. So that's going to be at C, and at A, and at C, and at A. All of these would have slopes of 0. I'm going to mark those there. So C, A, C, A, C, A, C, A. Then I want to look at the initial slope. The initial slope, so what this starts at is positive, and then it gets smaller positive. So that means I'm going to start here. And so I'm going to go acceleration. Slope of velocity time is acceleration time. Find your zeros. So these are all happening at B's, it looks like. So that's going to be 0, 0, 0, 0, 0, 0, 0, 0, 0. And then I'm going to look at my trend. So these are starting off my beginning slope is 0, and then it becomes negative. So that's going to be force. Force is directly related to which of these? Acceleration, right? F net equals ma. So force should follow along with our acceleration, and so it should look like the same shape. It doesn't have to mirror it exactly because and again, if you know calculus, you know that this is a sine curve. The derivative of sine gives us cosine. The derivative of cosine gives us negative sine. And then these two are the same. Kinetic energy. Kinetic energy is going to be the same as velocity. So K is 1/2 mv squared, but there's going to be no negative values. So if I look at my velocity graph, at B's, I have maximum speeds. I'm going to have maximum kinetic energies. And I have zeros at A and C. So it starts at B, right? So B, C, B, A. So this is going to be max, min, 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 max. Elastic energy should be the opposite of this. When you have all kinetic energy, you have no elastic energy. So that means that we're going to have peaks at the opposites. So where this is a positive, this is going to be 0, or maximum 0, maximum 0. And this is going to go The energy should be constant. It's just a vertical line as long as there is no conservative forces. No non-conservative forces. Elastic energy, we could also look at position. If you look at position, it has the biggest displacement at C and A, again, because it is kx squared. So it's going to be no negatives on that one as well.